Ngalakin kadijan yung boja.
We're now going to look at the situation where a semiconductor is in what is called non-equilibrium situation. We found that in equilibrium, the product of the free electron density, N, and the free hole density, P, is equal to a constant. And that constant is the product of the intrinsic population of electrons or holes squared. And we found that this was true regardless of the doping, whether it was N-type or P-type. So equilibrium is the state of a system in which there is no external influences. There is no change in the temperature. There are no net currents. Essentially, there are no external influences. When we have non-equilibrium conditions, then the NP product is no longer equal to Ni squared. And there are two possible cases. We can have a situation where we have the population being higher than the equilibrium population, where the NP product is greater than Ni squared. This is called injection. And the opposite case is extraction, where the NP product is less than Ni squared. Now we can talk about low-level injection, which is the main form of injection we'll be looking at in this unit. But in comparison, there is also a high-level injection. If we look at this figure, on the left here we have the case of equilibrium, and it's an N-type material, and we've doped it with dopant density of 10 to the power 16. So that means that the equilibrium free electron population is 10 to the 16. And we can find the free hole population from the NP product, which is Ni squared. So therefore our whole population in that case must be Ni squared on Nv. If we have low injection means we've increased the NP product, we've increased the density of holes, and we've increased the density of electrons. But because the density of holes is very large in comparison to the holes, the disturbance is negligible in the electron population. However, the hole population is significantly disturbed by 8 orders of magnitude. In the case of high-level injection, we have both the population of the electrons, the majority carriers, and the population of the minority carriers are comparable, of similar size. When we have low-level injection and equilibrium, we also found that when we look at the currents, the majority carrier current, the fusion current is important, and the drift current is important. But when we looked at the minority carrier case, with only the fusion current that was significant. The drift current for minority carriers is negligible. When we have high-level injection, where we have similar populations for free holes and free electrons, then all forms of the current are important for all types of carriers. So what is the process by which the whole population and electron population can change? When the product NP is greater than Ni squared, that is when we have injection, then there is a spontaneous process within the semiconductor to recombine the carriers. This is known as recombination. When we don't have enough free carriers, that is, the NP product is less than Ni squared, then the semiconductor will spontaneously generate electron hole pairs, and this is generation. In equilibrium, the generation of electron hole pairs continuously occurs, but the generation rate and the recombination rates are equal. That is, where we have the generation rate and here we have the recombination rate. And in equilibrium, these two rates are equal. When we have a non-equilibrium situation, then one of these terms will dominate. When we have excessive carriers, then recombination dominates. And when we have a lower number of carriers, then generation will dominate. So if we look at the case of an N-type semiconductor, the population of free electrons is given by the doping density Nd, which is significantly greater than Pn and Pn naught. And there will be a net recombination. So the symbol for net recombination is U. So we have a recombination rate that is greater than the thermal recombination rate, higher thermal. And that extra recombination term depends on how much the minority carrier, in this case holes, exceeds the equilibrium value. And the proportionality is inverse, it's an inverse proportionality to the recombination lifetime for the minority carriers, in this case the hole. When we look at the P-type material, and we have an excess of carriers, there will also be recombination, and this recombination will depend on the lifetime of the electrons and is driven by how many more minority carriers there are compared to the equilibrium value. So this is really saying that recombination in N-type material is controlled by the population of holes, and recombination in P-type material is controlled by the population of electrons. Now, there are a number of ways that free carriers can be generated or recombined. There's what's called band-to-band generation and recombination, where an electron somewhere in the valence band can go up into the conduction band and leave behind a hole and generate an electron in the conduction band. It's also possible to make this recombination rate faster by putting in an impurity in the semiconductor that has an energy level somewhere in the band gap. This then allows an electron to more easily jump into the trap level, the impurity level, and then jump into the conduction band. So this increases the rate of recombination. And this is called trap assisted or Shockley-Reed Hall recombination. Now we can look at the theory of these cases. We're not going to do that in this unit. We can come to a derivation of the lifetimes, but we're just going to accept that those numbers are given to us. In the opposite case of extraction, where we have the population of free electrons and free holes is less than the equilibrium population, then our next generation term U becomes negative. That is, we're getting generation. And that generation rate is given by the equilibrium population in I over twice the lifetime. So let's consolidate these ideas by looking at an example. So in figure 5 here, we're showing light landing on a semiconductor. So the light is being absorbed by the semiconductor. And the wavelength of the light is such that we can get band-to-band generation of electron-hole pairs. This means that the population of free electrons and free holes will be much greater than the equilibrium value. However, eventually we'll get a steady state situation where the rate of generation by the light will match the rate of generation that spontaneously occurs in the semiconductor. So after some time, when things settle down to steady state, meaning things don't change with time, we still have an external influence, but that's how it is different from equilibrium. Our external influence is, in this case, is light, and in steady state, things will reach a point where they don't change with time. And so the population of the minority carriers, in this case, the holes, will reach a new level. Now, this new level depends on the rate of recombination. So if we say that GL is the rate of generating electron-hole pairs, then we must, in steady state, match that generation with recombination. And so we can easily write down this equation for the steady state population of the minority carrier. And we see that it's a function of the amount of light that we put in the material. So the next question is, what happens when we turn the light off? We've had an excess of free carriers, and we turn the light off. Now the generation rate now goes to 0. And so we will find that there will be a change in the population. So now the recombination is continuing to occur. And so the differential equation that describes that case is this. The rate of change of the population will depend on the rate of recombination. And the solution of this differential equation is given by this function here. So in figure 7, we can see the effect of changing the minority carrier lifetime. The minority carrier lifetime is short, then when we turn the light off, then the excess generated electron-hole pairs will recombine and very quickly go back to the equilibrium value. So this must be our equilibrium value here. So the difference between equilibrium value and the excess value will eventually go to 0 at this point. If the minority carrier lifetime is longer, then it takes longer for the carriers to come back to equilibrium value. Now, in semiconductors, there is a situation where there are many defects caused on the surface of a semiconductor. And these defects can cause recombination at a faster rate than in the bulk. And this recombination depends on the area, the surface area. So here we have a drawing where we have X along this axis. And here we have an area where there is a surface recombination happening on the edge. We have light again coming into our bulk material. So a long way away from this surface recombination zone, we expect that the steady state value will be the same as the case we studied earlier. However, as we get close to this surface recombination zone here, there will be an increased rate of recombination, and so we expect the population to be less than the population a long way from the region. So if there is no surface recombination, we expect the population of the minority carriers to be the same everywhere. In the case where we have surface recombination, the population at the surface is less than the bulk. And we now know that this will cause a diffusion current. This will cause a diffusion current of holes towards the surface where the surface recombination is occurring. So we can analyze this situation using the continuity equation. But first of all, we define what is called the surface recombination velocity. So in a similar way where we had the bulk recombination rate depended on deviation away from equilibrium, it still depends on the deviation away from equilibrium, but it's the deviation at the surface away from the equilibrium that's important. And in this case, this term here, instead of being the inverse of a lifetime, is a velocity, because it's a surface area effect. And so we have SP as a surface recombination velocity. So our solution will be at the surface. We expect the diffusion of holes to the surface, given by this equation, this part of the equation, represents the diffusion of holes to the surface coming from the bulk. And this represents the recombination that is occurring at the surface. So if we apply the continuity equation to this result, so we cannot have an increase of the population of carriers with time in steady state anywhere. The recombination rate at any location is given by this term. So this is in the bulk area. So this is our generation due to light. And this is our recombination in the bulk. And solving this continuity equation, we find that it is a second order differential equation. And the solution of this equation is somewhat messy, but relatively simple to look at. There is an exponential term, which is depending on space, as we saw earlier. And there is a term that involves various constants of the material. These are various constants, so we can just replace that by a number. And again, we have the excess amount of carriers that are generated by the light. And we can introduce a term here, which is a square root of the diffusion coefficient and the minority carrier lifetime, and this is known as the diffusion length. So if we go back to our result, we see, yes, this is the exponential term represented in the equation that we derived. Far away from the bulk, we have PL. And this diffusion length term will be related to the slope at the origin here of this exponential function. So the diffusion length tells us how deeply this influence of the surface recombination has on the bulk. If the diffusion length is very long, then we'll find something like this. It'll go right into the bulk, and so there will be a population of the free carriers less than the bulk area. If the diffusion length is short, then the effect of the surface is fairly local, like this. So this diffusion length term is an important characteristic of the material, and we will come across it many times in our work. We can also inject carriers from a surface. In this case, again, we're going to inject carriers with light. And so now we're generating an excess of carriers at this surface here. So we have an excess of carriers. And over here in the bulk, we have our equilibrium population. So this will be here, not over here, if this is N-type material. Then, because we have an excess of carriers generated at this surface, there will be a diffusion current because of the population difference. And so we will get a movement away from the surface. So we'll eventually get steady state, and we'll find that we will get high diffusion occurring here, and as we move away, the diffusion current drops down to 0. So again, this situation can be solved using the continuity equation, and this is the equation that we arrive at, and this has this solution, which I'll leave you to look at. But again, we find that we have this diffusion length term involved, and we have this term that represents the excess of minority carriers. So again, we can take the slope at the origin, project it across, and so this distance here will be our diffusion length, LP. Now there are a number of exercises to test your understanding of this area of non-equilibrium case. I strongly suggest that you do these exercises without looking at the solutions. And if you find you don't understand something, then go back to the notes rather than refer to the solution directly. And if you still don't understand, as a last resort, look at the solution. And then perhaps come back a few days later and see if you can do the exercise without having to look at the solution. There's also some exercises at the back of this document, which are for students who have an interest or advanced students to tackle more complicated examples, but this is not necessary. It's really just for your own interest. You can see that the analysis is somewhat complex. So that's it for non-equilibrium situations in a semiconductor. So we looked at semiconductors in equilibrium, we looked at a semiconductor in non-equilibrium, and next we're going to look at a p-n junction, one of the fundamental building blocks of semiconductor devices. So that is it for today's lecture.